Today we talk about the second part of the lecture on neural network, where we will talk about multi-layer neural network. We have already looked at individual neural units and discussed that they can represent linear functions. But the main excitement about neural network is because they can represent non-linear functions. And we can represent non-linear functions by stacking layers of perceptrons into different architectures. So, today we will look at feed-forward multi-layer neural networks, which is a particular type of connections in neural network. Now, first of all, we will look at what are the limitations of perceptrons. So, we have seen that what we have really not discussed, but perceptrons have this monotonicity property. So, in a perceptron what we are doing is that we have an input and we have multiple outputs and we have weights associated with them. And because of this type of connection, perceptrons have a monotonicity property. If a link has a positive weight, activation can only increase as the input value increases. So, it cannot represent functions where input interactions can cancel each other. So, each input is individually interacting with the neuron. So, it cannot handle interactions between the network. For example, perceptrons can be used to represent gates like AND. Suppose you have an input and you want to output 1 if all the, suppose there are two inputs x1 and x2, you want to pass 1 if both x1 and x2 are true. Then you can set the weights and the threshold such that the result will be 1 only when x1 and x2 is 1. However, perceptron cannot represent the XOR function. In XOR function, suppose we have two variables x1 and x2, which can take 0 and 1. In XOR is true for, in this case it is negative here and here. So, XOR function is not linearly separable and it is not monotonic in the individual inputs, and it cannot be represented by a perceptron. So, a solution to this is to have a multi-layer neural network, where we have these units stacked on each other. So, we have these inputs. So, we have x1, x2, x3, xn as the input, and we have, let us say, one, this is the first layer, we call it hidden layer 1, and it has units, let us say z1, z2, z3, zl, and then there is the output layer where we have units y1, y2, right. Now, we have inputs feeding through from input to this layer and etc. And then from here to this layer, right. So, we can have a multi-layer network where we have the input layer and the output layer, and between the input and the output we can have other units which are called the hidden units. Why hidden? Because in the training examples they are not observed. We have the input and the output, these are called the hidden units. And through these hidden units, we can represent many non-linear functions. For example, if you look at this picture, we have x1 and x2, and each of z1 and z2 is a linear function of x1, x2. And then y is a is a linear function, it does a linear separation between x1 and x2, but y is a function of z1 and z2. And if we use suitable nonlinear activation functions, then this sort of connection can represent XOR or other non-linear function. So, we can look at this expression of what multi-layer networks can express. We have seen that single layer networks can represent linearly separable function. Multi-layer networks can express interactions among the input. In particular, a two-layer network means this is a two-layer network where you have one hidden layer and one output layer. This is the input, this is a hidden computing layer, this is the output computing layer, and these two-layer neural network can represent any Boolean function. And continuous functions within a tolerance, provided of course you have the requisite number of hidden units and you are using appropriate activation functions, then all Boolean functions and all continuous functions within a certain tolerance can be represented using two-layer neural networks. If you have three-layer neural networks, then you can represent all computable functions. So, these functions can be represented using two-layer and three-layer neural networks. So, they have very good representation capacity. But the next question is it learnable? Just because a representation exists to represent a function does not immediately mean that you can learn the function well. But for neural networks like this, learning algorithms do exist, but they have weaker guarantees. In perceptron learning rule, we said that if a function exists, then this procedure will converge. So, for multi-layer neural networks, we cannot give such strong guarantees, but algorithms exist and people are working on different very exciting types of algorithms. So, let us look at a general structure of a multi-layer network. This is a three-layer network where there is the input, then we have the first hidden layer, the second hidden layer and the output. This is an example of a layered feed-forward neural network. This is a feed-forward neural network because the inputs, these connections that we have drawn are single directional. Input to first hidden layer to second hidden layer to output. All the edges are single directional and it is going forward from the input to output. There is no back link. So, this is why it is called feed forward neural network. This is called a layered network because we have organized the neurons into layers and layer I is connected to layer I plus 1. Also, this particular diagram shows a fully connected layered feed forward network where there are two hidden layers, one output layer and of course, the input layer is there. So, in this particular type of feed forward neural network, the input will be going from feed forward from input to the output through the hidden layer. Now, while talking about perceptron training, we said that based on the error in the output, we change. If we observe there is an error in the output between what should be the ideal value and what is computed, then we change the weights of these connections so that that error is made smaller, right. So, that is what we looked at in perceptron training. Here also we need to do the same thing. However, here there is one difficulty. We know what should be the ideal output here and the ideal output here. So, based on that we can change these weights, right. But at the hidden node, the ideal output is not told to us, it is not known to us directly. So, on what basis do we compute these weights? We know the ideal output here, we can compute the error directly and on that basis we can update these weights. But we need to know what is the error here. So, what is done is that the error that is observed here is propagated backwards. So, the assumption is the error here is a result of error here, here and here, because these are the 3 nodes that are feeding input to this node. So, this error here is due to errors here, right, and therefore, what we do is that this error we now back propagate to these nodes. The error here also we back propagate to these nodes. Based on these, each of the nodes we know what is the notional error. Based on that error, we update these weights. If there were more layers here, the error here will again be back propagated to those other nodes. So, the error signal flows backward. The computation in the network is forward, but the error signals flow backward, based on which, based on this computation of the error signals, we figure out how the weights have to be changed. That is why the method for updating weights in such multi-layer neural network is called backpropagation. Okay. So, the error signal is flowing forward and the input is going forward and the error signal is going backward. So, these are the steps in the backpropagation training algorithm. First step is initialization. We give the structure of the network and we initialize the values of these weights, and usually we give these weights small random values. We give them small random values to the weights and different biases in the network, right. Now, after initialization, we do the forward computing. Now, what we do is that we take our training example, which comprises x1, y1, x2, y2, xm, ym. So, these are our training examples. We take the examples one by one and apply them to the network. We apply x1 to the network, we get some output y1 hat. So, given x1 we get y1 hat. So, this is the output that we get, and the ideal output is y1 hat, y1, and let me write it here. So, the output that we get is y1 hat, here we get y2 hat, here we get ym hat for a particular configuration of the network. And if this y1 hat and y1 are different, this is different, then we look at the error and based on this we change the weights. So, we in the forward computing, we apply the input first to this layer. Here we first take the summation followed by the activation function, we get the output at this layer. We get the output z1, z2, z3, and then based on that we compute y1, y2, etc. as this is computed as the activation function applied to sigma wi zi. Right? Here it is activation function applied to sigma xi wi. So, we get do the forward computing. After doing the forward computing, now we have to update the weights. So, as I said that we can update the weight at the output layer in a similar fashion as we did for single layer units. If you think of, you have single layer sigmoid units, we have already worked out how to update those weights. Right? So, these weights, suppose let us say this set of weights we call them W, and this set of weights we call them V. So, W is updated using the sigmoid layer training rule, which we discussed in the last class. But how to update V? As we said that we do not know the target values of Z1, Z2, Z3. So, what we do is that we back propagate the error here to the error here. So, we propagate errors which are visible at the output units to these hidden units, and then based on that error we do the similar training rule. And if there were more layers between this and the input, so these errors can be further propagated in this direction, further propagated downwards. So, error back propagation can be continued if the net has more than hidden layers. Now, we will have to see how to compute the errors, and for that let us try to do the derivation of this computation. Now, for the output neuron, so the error function is E equal to half sigma y minus y hat whole square, and we can take summation over all the training examples if you wish. Now, let us think of, in the network we have different units. These units are either at the output or at the hidden layer. So, let us take any unit j. So, for each unit j, so j is a unit, and for j the output is oj. So, first of all, we have seen that in the unit there are two components. One is the summation component, the second is the activation function component. So, first the summation is applied and then the activation function is applied. Let us say that output here we call net j, and output after this we call oj. This is a unit j. So, the output of the summation is net j and output of the final output is oj. So, oj equal to, so for unit j, oj equal to phi of net j, and net j equal to summation wi xi, where I ranges over all the inputs to the unit j. So, this is equal to phi of sigma k equal to 1 to n. So, k ranges over all the input wkj ok. So, wkj is the weight from the unit k to this unit j, and ok is the output of unit k. So, output of unit k is an input to unit j. So, suppose this is a node which is j, and this has these three inputs 1, 2, 3. So, this is W1j, this is W2j, this is W3j, and the output is here O1, O2, O3. So, this is the output computed as unit j. Now, if we want to find the partial derivative of the error with respect to wij, we get this is equal to del E by del Oj by del net j by del wij. So, simplify the computation. We have used the chain rule to write del E, the partial derivative of the error with respect to wij, as the product of these three partial derivatives. So, to make the computation simple for us. So, this is my j, this is my unit j, and these are the units which are feeding to this unit. This is the unit I. Okay. And j has initially the output is net j and then the output is oj. So, this is oj and this is oi. Okay. Now, we have decomposed this partial derivative in these 3 components. Now, what we will do is that, let us remember this, and we will do these 3 computations separately, then we will write them together. So, first let us look at del net j by del wij. Del net j by del wij. So, what is net j? Net j is sigma oi wij, right? And so, we have del wij sigma of wkj ok, k equal to 1 to n. So, this is equal to oi, because only here we have wij, and these other link 1 to n, they have nothing to do with I. So, del net j by del wij is simply oi. Okay. So, in corresponding to oi only we have wij oi. Okay. And we have O1 w1j, O2 w2j, O3 w3j, they have nothing to do with wij. So, only here we will have one term, and so this is equal to oi. So, del net j by del wij, this we have, this part we have computed, and this is equal to oi. Let me clean this so that we can work out the other 2 components of this expression. Next, let us take this second term, del oj by del net j. What is oj? Oj equal to phi of net j. So, del net j, we have phi of net j, and so we have already seen that this particular derivative will depend on the form of the activation function. If you assume sigmoid activation function, for sigmoid activation function we will have this is equal to phi of net j 1 minus phi of net j. Okay. So, this is the second term here which we have computed, given like this. Now, let us look at the third term, del E by del oj. Now, we can take the derivative with respect to oj, and we can get a recursive expression of the derivative as follows. This is equal to summation over I. Now, first of all, let us say that the inputs to this network are 1, 2, 3, 4 up to n. So, let us say z equal to one to n. These are the inputs to the unit oj. So, we can write this as follows, summation I. So, del E oj, before that let me write this. So, this is E of the output oj is equal to, this error is dependent on or rather let me just do it, write it in a proper way. So, it's not the other, it's the other way around. So, this error at the unit OJ has come from the units which are upstream of OJ. So, if you allow, let me rub this part so that we can make the drawing here. So, this is the unit J, and J has certain input which we have already seen, but J outputs to the next layer, right, and let the output of J go to the input of these units, and let us call this set of nodes Z, and let us say that Z comprises of Z1, Z2, etc. Or just for simplicity, let me denote it, for this step as 1, 2, L. Okay. So, these are the nodes to which the output of J is feeding, and therefore, during back propagation, the error at these nodes is due to the error here. Okay. So, the error of OJ is based on error of net Z1, net Z2, net Z3, right, or for simplicity let me write net 1, net 2, etc., net L by del OJ. Okay. So, now this error, so these components due to net 1, net 2, net L, we can do a summation. So, we can write this as, let me again compact it, error of 1, 2, L, and this we can write as summation over L, this index, let us call it ID, or let us use L as the index, and L we have del E by del net L, del net L by del OJ. Okay. So, this error is coming from these units, and I am taking the summation over that. So, summation of del E by del OJ, del E, where it is coming from this unit. So, we were writing it in chain form as del E by del net L by del OJ. So, for this node we have net 1 and then O1, net 2 then O2, net 3 and O3, and the output of this contributes to the net 1, contributes to net 2, contributes to net 3. Okay. So, now what we can write is that this can, so if we look at this, so we can write this as summation of over L del E by, so let us look at the output here. Output here is OL, so we can write it as del E by del OL by del net L. So, this part I have expanded to del E by del OL times del OL by del net L, and we have del net L by del net J. So, del net L by del Oj. So, net L will depend on sigma Wjl Oj, right. So, from this we get Wjl. So, this component is equal to Wjl. Okay. So, we have this expression. So, we can compute this derivative with of error with respect to Oj if all the derivatives with respect to the output of the next layer are already computed. Now, so we can write this as, so suppose we have del E by del Wij equal to delta J Oi. So, we have the output of the current unit and the delta or the errors which are available here. These errors are the errors which are available here, which is being proper, which is being contributing to the error here. Right? So, this delta J corresponds to the error which was computed at this layer, which is brought here. And the component of this delta J are, so delta J is one of these units and its component is del E by del Oj times del Oj by del net J. And this will have, this will be treated in different ways depending on whether the unit is the output unit or it is an intermediate unit. So, if it is an output unit, we can use the formula which we have already seen. So, it will be equal to Oj minus Tj. Tj is the target output at that node, which we wrote as here. So, Tj is the target output. So, Oj minus Tj times Oj times 1 minus Oj. This will be if J is an output neuron, and if it is an intermediate neuron, this will be equal to, it will get the outputs from the next layer, get the errors or the delta values from the next layer as we have written here. So, it will be sigma over the set Z delta L Wjl times Oj times 1 minus Oj, if J is an inner neuron. So, this delta J is, if we are looking at for the output neuron, we have already seen this delta J equal to this, but for an intermediate neuron, it comes from this formula where we will get delta J as sigma over Z, where Z is the set of those units to which this unit feeds input. So, sigma over Z, the delta of those nodes, the errors computed at those nodes, times Wjl times Oj into 1 minus Oj. So, this particular part, this comes due to the sigmoid activation function. If we change the activation function, this will be a little different. So, this is the basic derivation using which So today we stop the class today, and in the next class we will look at how this is incorporated into the back propagation algorithm. Okay. Thank you very much.